Welcome back and welcome to Session 3, Artistic Impression. This duet is dedicated entirely to the arts. It elaborates on the interface between music and fine arts as combined with technology and artificial intelligence. Both lectures raise fundamental philosophical questions about the relationship between humans and the machines, in terms of artistic considerations, motivations, intense and finalized production. Join us to understand gridded interfaces in the sounds of electronic music, followed by gridded interfaces in computer-generated art. Our first speaker is Professor Dr. Joseph Gondla, who lives in Graz, Austria. He holds a PhD in medicine and is a sound and media artist, maker of software and electronics. He is a visiting professor of sound design at Donau University Krems and assisting professor at the FH JOANNEUM University of Applied Science. He teaches sound and interaction design, workshops on topics like improvisation, software and electronics for designer and artist. His multidisciplinary journey sways between software, music, new media, and art, like music for computer games, theater, film, media, and sound installation. What a journey it is. Main instruments are guitar, electronics, and software. So let us welcome Professor Joseph Gondla. Hello.
Thank you very much. Hello for this warm welcome. And I want first to thank also the conference team for your great work and for inviting me to this conference. It's really a shame that I cannot be there in person, but this is how these times are at the moment. As we are really short on time, I start immediately. So I will talk about, as you already mentioned, the grid in sound. And one of the main proposals to this short presentation is the statement that what we make makes us. So I will talk about grids, grid interfaces, and their influence in music and on media, and especially also on the performance. But first, so that you get the raw impression how our surrounding and how our tools, which for me are a bigger extent than just a hammer or something, but also our surrounding and everything we work and live in, is shaping what we are doing. This citation, what we make makes us, is from Ji Wang, a professor, musician, computer scientist at Stanford, and also the author of the readable and recommendable book Artful Design. Now, first, let's listen to a little bit of sound. So, very short, first example, what we heard was water drumming. And this is one of the examples how music is related to the environment, not only to the water, but also due to the fact that it is performed in open air, it led to music which was mostly related on rhythm. Rhythm needs a non-reverberant room so that you really can hear this kind of rhythms. Many of you might have experienced already bad acoustics in a rock concert where the rhythm was basically clashing against other things. On the opposite, if we perform music in big venues, like in ancient times in churches, we might hear something like this. So here we heard the fact that a big reverberation acoustic room leads to the overlapping of the voices and thus also to music which is more harmony related and cannot perform sophisticated, complicated rhythms. But back to the grid. Musicians have been dealing with grids since the first efforts of transcribing music. So the oldest known musical notations followed basically a timeline approach with a pitch approach. If you're looking at these images here, you see on the right upper side, you see JOANNEUMs, one of the first written down notations which have no bars or rhythmic structures, and the same with the Gregorian chart. But the grid is clearly recognizable up until modern staff notation on the left upper side, or even more modern, as you see down here, ASCII-tab notation, which is now used in computers, mostly to show the fingering for guitars or chord diagrams. This goes back to as old notations in grids, rooting in these organ and lute notations as early as approximately 1300 after Christ. So grids in music basically are applying a discrete raster on the continuous artifact of sound and music. But what about the instruments? So we look at instruments, at first these instruments might have looked like this. On the upper side we see a keyboard, but it's not an ordinary keyboard. What we see here, we see split keys due to the fact that in natural tuning notes are not the same. So the natural tuning grid is not the same if, for example, we sharpen a note or if we flatten a note. So we have this split kind of notes. The other way to deal with natural harmonics was to use non-fretted instruments which could play different tones in between these. But at least the so-called well-tempered tuning came into place, and this was then helping musicians and making musicians capable of playing notes in different keys. Very famous piece by Bach was dedicated to this kind of stuff. His well-tempered clavier, as you might know it, was dedicated to this technology that you could now play all this stuff in all 24 keys. But what does this tempered mean? This tempered comes from Latin, temperare, to mix, and this means that we had to mix notes, frequencies, which before had been separated into one. So to say, very roughly, it's not the mean, but the best mix of what's happening, so that we could play only one note and then transcribe or use all the possible keys. For me as a guitarist, this grid was always visible on the fretboard. The fretboard is basically a strange thing for guitarists, because the same note appears twice on the grid, not as in a linear keyboard, due to the fact that it's two-dimensional and the pitches of the strings overlap. We have the same notes on two different parts, which gives, for, at least for me and also in my knowledge to other guitarists, a complete different sense of pitch than, for example, at the keyboard player. So after these instruments have been developed, we had the well-tempered tunings. There was a urge and a need to fix down music for mechanical, later on electronic and computer music instruments. So to do this leads to different kind of methods and grids. What we see here on the upper left of the image, we see an old piano roll. This was basically fixing music in a two-dimensional grid, so you had the time and which pitch. It was not capable of notating, so to say, or controlling the velocity, the loudness of what was played. This kind of technique was also later used in computer punching cards, where we have no clear coincidence between the music it played and the data it stored, but nevertheless, here already we had a three-dimensional, even if it's in a two-dimensional grid, representation of music, because music basically, as in this lower graphic is shown here, consists of three dimensions: dimension of time, dimension of pitch, and dimension of timbre or color. Then, coming up with electronic interfaces, there was the problem how should we deal with this kind of interfaces. Now, if we look at the computer, and what we see here is one of the oldest, not really the oldest, but one of the first big computers especially made and dedicated to making music. It's from 1951, so a long time ago, the so-called RCA synthesizer from Australia. And here, as this was basically made by engineers, we already see clearly again rows of knobs and switches as engineers' heritage and typewriter keyboards. So these were, so to say, the first interfaces already giving us the heritage of grids to deal with music, which basically, or sound, which basically is a continuous signal, which was then, so to say, transformed into a discrete signal so that we could handle it in the computer. Later on in software, this showed also up as a piano roll, which is a strange resemblance to the old piano rolls, but could, of course, represent much more dimensions than the paper one. If we look at interfaces of machines, computer music machines and software, we often will experience this kind of grids. So here are 3 examples. On the upper right side, it's one of the first really common available and usable computer music software, because this big kind of stuff, like we see here, was only available for academic stuff or maybe really rich people. So the common musician, the common composer had to deal with stuff like this, which was one of the first sequencer softwares, Steinbeck's 16. Also here we see that it was developed not by maybe a designer or artist, but by an engineer. For me, a little bit resembling also to this grid, which is one of the control stations of the former flying above us spaceship Mir. Nearly not together, but at the same time, when software sequencers came up and these parts of grids were showing up all over personal computers, which at this time were not capable of really of playing sound, but only of triggering machines who generated sound. This kind of machines also evolved, which is a drum machine, one of the first really usable drum machines, the Lin M1. And also here we see again, mostly engineers did designers with some not really user interface designers, but already besides knobs, like here we have on the software interface, we have only kind of discrete values to punch in. Here we already have continuous controllers, like in these faders or these knobs. But besides this, it's a push button device. Now composers at this time and also before, with the rise of electronic instruments, were saying that the well-tempered tuning and this kind of discrete pitches, harmonies, etc., are maybe too constraining. So there was also an effort beside the grid, where instruments with continuous controllers like the Telharmonium, this one here, or the famous, or it's also called Termenvox or Theremin, was a desirable path to go. Or like the Ant synthesizer, a Russian model where you could draw sounds. Or later on, the famous UPIC system by Yanis Xenakis, an interactive environment intended for a sound-oriented multi-scale approach to the composition of music. This was really successful, both of them, until later now personal computers became so capable of generating sound and music that they became obsolete. But at this time, when people were dealing with this or this in academic and university and research centers, ordinary musicians had to deal with interfaces like this, and even then they were lucky because this costed approximately the price of a little car at this time, so that you could cut music on a just vertical grid in the time domain, as in former days we did it on tapes. And this also led to a very tape-orientated music, especially in the so-called new music or classical music, whereas in pop music already the urge came up to split this into little loops and making pattern-generated music. But for this, another thing had to come up on the scene, the so-called grid interface. And before grid interfaces really became increasingly popular and were everywhere because they are, as we will see, full of light and color, and they can do nearly everything. They are the input devices and display devices, but to pave the path for them, a special software had to arise. And this was Ableton Live. Maybe some of you use it. When this came up, I have to admit personally, I was not impressed because I'm not a musician dealing so much with patterns and loops, at least not at this time. But this was really the first thing who completely revolutionized the scene. It was designed by Robert Henke and Bernd Roggendorf, and it was deeply rooted in their experience as live electronic musicians. So they used first self-made software to prototype this, and then it was developed by professional engineers, of course. Interesting fact is that also a painter was responsible for the interface, Mr. Thorsten Slama. And what we see here is the so-called grid scene view, where you have these clips which you can trigger and control and manipulate live in real time. So first software for ordinary musicians to come on stage, because before DJs and musicians on stage were basically working with stuff like this. So they were playing tape loops, tapes and mixes, but not really interacting with clips and little short loops, drum beats, etc., live on stage, and the audience also seeing that they do something. But interacting with a mouse and a keyboard with this software was not really the most perfect way to do it. So what has to come up? Before software, there was a hardware solution. It was a very famous and now very valuable machine, due to the retro trend also very expensive at the moment. It was this RKMP60. This hit the market in 1988. So here we clearly see a grid of 4x4 pattern hitting special drum samples. So with this you could play basically a virtual drum, store sequences, play them, and later record them, and later on play them. This model is still used today and was very famous. We might not have time, but if you have time, listen to DJ Shadow's sampling masterpiece, Introducing. You get it on YouTube. So very commercial product. And then it had the Silverling later on, a very simple one, which also, like Ableton Live, made a big impact on the scene. And this was the Monome. The beauty of the Monome and the grid of the Monome, later firstly called only Monome, later on called Monome Grid, was its simplicity. It could be everything from display to controlling any piece of software, not dedicated to a special piece of software. Now, just very shortly an example so that you also see how it works. Not very exciting, just a short demo how the Monome Grid was working. Okay, that's enough. So I think you got an impression how this Monome works, and also about the beauty of its simplicity. If you also saw, like I saw, colored LEDs this is an artifact of the streaming. It should be only red, little red lights, only one color. But soon after this project, so to say, because it was also open source and it pushed a lot in the DIY scene for building their own interfaces, a commercial clone came up, which you see here now, the Innovation Launchpad, explicitly dedicated to interact with Ableton Live. So now you had a physical representation of the grid in software in hardware. On the other side, people were not content with this and thought this is just, again, a push button device. And they were more about playing live, playing with so-called controllers, like also the Launchpad was called. This led to funny stuff like this kind of controller rhythm. On the other side, people really tried hard to come up with an artistic way and a way that showed that they are really trained, skilled musicians playing this kind of instruments. And now I want to show you a short example, not of playing these controllers, but of so-called finger drumming, interacting with a small grid of pads and what this can achieve. This is Mr. Keo Neu in one of these finger drumming performances. So my time's nearly up, so I have to hurry up a little bit. This was the one side of the development. On the other side, people again wanted to go away from computers, going back to electronic instruments, using stuff which, in my opinion, and also in the opinion of others, is more related to stuff from the 60s, 70s, and 80s of the last century. So they used again so-called analog modular systems, like we see here, a Töpfer sequencer, also forcing again rhythms and pitches into a very narrow and fixed grid of knobs and switches, which you could pre-program and then play afterwards, play on your music. This led, ironically, not only to really clear pattern-oriented music, but to music of long evolving rhythmic patterns, due to also the fact that you could somehow randomize this kind of grid-controlled systems. Also, as these systems were expensive partly, it came back into software, like the VCV rack, which you see here, but here also we see the classical principles of organizing interfaces in rows, etc., etc. Now, why do we like grids so much? How do we perceive them? On one side, if we perceive something, we have two ways. We have bottom-up information and top-down information. So to make a long story short, basically we extract features, we are searching for patterns, and then we try to find in our visual memory special models of these patterns. And the grid is a very simple model, which is not a three-dimensional model, but a two-dimensional, but nevertheless helps our perceptive system to decode as fast as possible what we see. This also resembles, of course, to Gestalt principles, so that we can ascribe special graphic codes, which we see in switches and knobs, to special semantics on our machine. Which on the way leads us to how do we interact and design these interfaces. So, as you might know, the scheme of Bill Verplanck, how bands interact with the world. We have basically two metaphors. We have handles and buttons. Handles are more for continuous interacting. Buttons are triggering something. We have media which we interact with, which we can change or we cannot change, hot or cold media. We feel about it and we know about it. And the map is basically the closest resemblance to a grid. So if we are experts in using something, this map is the most valuable instrument to interact with this kind of stuff. So just an example here, a sketchbook of an interface designer in designing interfaces for electronic music, which at the end then looked like this, for example. But here still we see clearly structured, again, grids, has its own affordance, but also limits, of course, what we can do with it. Now, what's happening nowadays, I'm soon come to an end. Nowadays, this kind of is all flowing together. So newest machines like this so-called Machine Plus from Native Instruments, we see grid interfaces, we see knobs, but we also see the coming back of screens. And these screens basically try to make the computer invisible so that we don't have to use laptops or other stuff on stage anymore. As the time is already progressed, I skip the example how you interact with this. It's nearly the same, just 1 minute. Also here you see basically same as finger drumming. You can make very skilled things. Okay, and what's happening now on this scene? On one part, these grid controllers are clearly established as performance instruments on stage, influenced what we did. On the other side, there is a kind of baby facing happening, making things thinner, like this pocket operator, also a drum sequencer and machine in the size of a pocket calculator, or even smaller, this kind of stuff, the Teenage Engineering OPZ, which is a complete recording studio, sampler, etc., in one tiny little gadget resembling the size of a remote control. I will not play you the demo now. So basically, I'm nearly at the end of my presentation. So which started with what we make makes us, which is resembling to an older citation, we shape our tools and the other our tool shapes us, which is ascribed to McLuhan. And this principle, of course, applies to music machines and music software. The grid constraints the possible artifacts which we can produce, but provides also very practical means to interact with the machines. It also opened up the possibility for non-trained people who are not trained musicians to interact with these machines and to make music, so the democratization of music. So, yeah. On the other side, some people think this is something like a Prokoustres. So if you might know this famous citation, if all we have a hammer, everything looks like a nail, might be also true for grids for electronic instruments. So we have also trying to cross the frontiers and to expand these grids beyond just regular 4-to-4, 8-to-8 grids or anything else. In this way, to a more elastic interface, still dealing with some rasters and grids. So, Tuda, and thanks for your attention.
Toda rabba, and thank you, Professor Dr. Joseph Gondla. Thank you very much.
You're welcome.